Hey, John here. Let's talk about inheritance. Before we do that though, let's review where we were from our last video, all right? A little terminology we want to make sure we understand. Remember our date class, okay? I clean it up a little bit, but it's otherwise the same thing. And we remember our employee class, all right? Now, what can we say about these member items, these data member variables in here, okay? When you speak of an employee object, an employee class, you say an employee has an employee name. An employee has a hiring date. Okay? An employee has these attributes, these items, these features. Okay? We don't say an employee is a hire date. We don't say an employee is their name. All right. If this was a piece of let's say this class was designed to model an orange. All right. You could say an orange is a piece of fruit. An orange doesn't have fruit. An orange might have seeds, right? But so do bananas. So you might have an orange that is a fruit. You have a banana that is a fruit. How do you model this other relationship is what we're getting at here, okay? This is what we talk about when we, this is what inheritance provides us, all right? So I've created a more abstract class here so we can watch how this works. This is just something. Call it a foo, all right? It has 3 different constructors. And each one of these sets I to a different value in its initializer list. I do this only so that later on, if we print out what, the current I value is, we'll see a different thing based on which constructor was called. And in particular, when we destruct it, we can say, oh, by the way, when I'm destructing this foo, it was one that was created, when I was 2 like this. It used this version, all right? We also have a couple of methods down here. Let's talk about this for a second. It may seem foolish to provide a get and a set down here that does absolutely nothing other than just return the value and set the value. You might argue, why not just make these things public? Because, in reality, not even in theory, I'm letting anyone do anything they want with these variables by providing these get and set accessor methods, all right? Well, the get accessor and the set mutator, that's what people are talking about when they say mutator, something that changes the thing. All right. Well, the reason we do this is because later on, when we're debugging our code, and you've got 1 million lines contributed by 100 other people, you can do something like this. Let's say you find out when your program is used, this J value becomes problematic for some reason. During the evolution of your project, even if it's hours, years, or whatever, it might be noticed that the J value is only valid when it's, say, less than 100. So you might want to add something like this. If J is greater than or equal to 100, do something. Maybe you want to throw an exception here, right? Or something like that. This gives me the ability to add this logic right here that I otherwise have no way of doing. If I force everything everywhere that ever wants to touch J, or even read it for that matter in this example, we force them to execute these functions here. Even if the function lets them do anything they want, it gives us the ability in the future to put a gauntlet in here to prevent or at least monitor and report on things that may have gone awry. Or it might actually be that you knew on day 1 that you want to check for J less than 100, and that, 2 years from now you realize, oh, I need J to be less than 200. I can change that. I can do it right here one time and not change any other code, and all the other code is then, subject to the new rule. And you know that for an absolute fact because these are private, and by definition, no one can touch a J unless it's a member or a friend of this object. So it gives you a very narrow place to look to make changes and to evaluate failures when they happen down the road. All right. I just wanted to point that out while we're in here. And you can see you don't necessarily have to use it everywhere. It helps if you want to be able to do what I just showed you, right? Because set j to get j times 2 is really saying j equals j times 2. All right. Or even simpler, you could say j times equals 2, and that's a lot easier to write than providing these accessors down here and then calling them, right? It's even easier to read, but in the long run, you're better off having all the protection that you need in there. Now, another thing, a lot of people might say, oh, it's inefficient to have to call functions and subroutines when all you want to do is grab the value. Your program will run slower. Au contraire, in this particular case, if you write it like this, these are what we call inline functions. So if they are minimally implemented like this, these will be completely optimized away by the compiler. In the end, these are exactly the same when your program runs as if these were public. There will be no difference even in the executable binary, okay? As long as these are inlined like this. And they still give you the opportunity in the future to change it if you want. All right, so that's enough of that. So what does this thing class have in it? A couple of different constructors, and it has 2 different methods, and they both print out different things, and they diddle with J just to have them do something. And then down here in the main, we create one, and we give it a 23, so it's going to use the constructor that has an integer, this one right here, okay? And then we call the F1 method right here on that, and then we return. And when this function returns, this variable here goes out of scope, and it'll be destructed. And because we print a little message in every one of these methods, we can see what's going on when it runs. So let's make sure it compiles, and let's run it. And it does exactly what we thought. It prints out, hey, I'm in this constructor, and it's the one that has the integer, right? Then it says, oh, I entered my F1 function, and then when it went out of scope, it said I've been destructed, and by the way, I is currently set to 2, and that's what we did in this function here. So that all works just to get our bearings right, okay? Let's look at a variation of this. So this is the same class foo that we just looked at with our little guarded protection thingy down here. What's this all about? So here's the inheritance, all right? Let's go down here to main real quick and see what we're doing. Again, we're going to create a foo, and we're going to do this. Then we're going to create something else, and we're going to execute methods on that. So this is the whole goal, right? This is where we're heading. Now let's look and see how we're going to get there. Okay, so bar. What is a bar? See this thing? We've added this colon foo. What we've done is say, look, I'm going to create a bar, just like you've done all semester long. I want a class called bar. By adding this colon and saying bar is going to inherit everything that is foo. And these are the types of words and phrases that you hear people say when they're talking about inheritance. You say that a bar, this bar is derived from foo, okay? It is a subclass of foo. And in this analogy with the orange and the fruit, this would be the fruit, and this would be the orange. So what we're really looking at is bar is a more specific variant of foo, right? An orange is a very specific thing, as in contrast to the general description of what a fruit might be, right? So bar is a subclass of foo, and because it's a subclass, then foo must be the superclass of bar. We say foo is the parent of bar, therefore bar is the child of foo, right? And we refer to foo as the base class of bar. All right, so this is all the kind of words that you might hear. Let's look and see what a bar then is. We have a bar as a default constructor, and our initialization list will set the A member, the private member, to 123. And then we have this over here, all right? Now, if bar wants to construct itself based on a foo, and when the foo part is initialized of bar, right? So bar is a constructor, and what it needs to do is make sure that a foo, its parent object, also has to be constructed, all right? So in the initializer list, I can say if I want to, by the way, when you construct the parent portion of my bar class, use this constructor with this argument. All right, we'll change this in a minute and you'll see how that changes, okay? So this simply says set A to 123, and when you do the parent object, do it like this. We'll then print out a message. In the destructor, we're going to print out just like we did with the foo. We're going to say, oh, by the way, A is this. We're not going to ever change A, so every time this thing is destructed, we should see A would be, in this scenario, a 123. There's really no way to change it. There's just a little contrived example, all right? And it has a member function called F3 that prints out a few things, all right? One of the things it prints out is the J that it inherits from its parent. So let's look and see how some of this stuff works, the grammar of all this, right? So when bar is created, he wants to use this constructor. If I don't put foo, you know, whatever I said in there, was it 123 or something like that, or a 100? Then the compiler would use this one. All right, or if I gave it a text string, it would use that one. That's not a big reach, right? Okay, then what happens? Well, because bar is a foo, all the methods that foo has are also now methods of bar. So when bar calls getJ right there, he doesn't have one in here. Well, where does it come from? He inherited it from its parent. It's going to call getJ in its parent on behalf of itself. That's what's going to happen in here, all right? So now what happens down here? Let's go back in here. We're going to create the foo, and we're going to execute this member function, just like we did before. We would see the same behavior. No change in foo, therefore this will do the same thing. But what about this bar? I'm going to create a bar, and then I'm going to call F1, F2, and F3. Well, just like when bar decides he's going to call getJ, and getJ is public, so he can do that, right? All these guys down here are public, okay? And bar inherited F1 and F2. There's no reason that anybody that creates a bar can't call F1, F2, F3. You can call getJ and setJ, all right? So let's make sure that works. Good. Yeah. What am I looking at? Here's this one. So there's a lot of noise coming out of here, all right? What happened? Remember, we created a foo, and we called F1 on the foo, all right? In the end, the foo gets destructed down here. Let's comment that out so that we can keep an eyeball on the bar object, right? We don't really care about this right now. Let's not concern ourselves with it and get rid of some of the noise. All right, let's rerun inherit one again. Okay, so what happens now? You still see a foo being constructed. Well, of course you do, because when bar is constructed here, the first thing that happens is its parent object has to be constructed. Bar doesn't construct its parent. It inherits its parent's construction, all right? When the parent construction is complete, then the child's construction method will be called, all right? So these two lines here are both printed as a result of the bar right here being constructed, okay? First thing that happens is it comes in here and it says, I want to construct this bar using the default constructor because I didn't give it any arguments in here. It's the only one it can use, right? Its initialization list says before I do my construction in here, which doesn't do anything but print, the first thing it does is it sets A to 123 here. And it says my parent object needs to be constructed like this. So all this stuff here is done prior to the body of the bar constructor, and you saw that. That's why this gets printed first, and it's also why we have an integer in there, because that's the one we told it to use. Let's change that by just removing this, right? What if I don't put this in here at all? What's it going to do? Well, it still has to construct its parent, and I didn't tell it what to do, so it'll use the default constructor, okay? You'll see it construct it this time using the foo that has no arguments. And as we recall, it sets I equal to 1 when you use this constructor. So down here, you can see it printing out the 1. Previously, it printed out at 2 because we set I equal to 2 when we use the constructor that took the integer like that, right? So again, let's keep our bearings on what we're doing here. Let me put that back the way it was. All right, so this is how you tell it which constructor to use when constructing the parts that you've inherited, okay? After we're done, we say, look, I'm a bar, and I am everything that is a foo and more. What else do I get? I get my own constructor, my own additional member variable. I have my own destructor, and I have an F3 in addition to what I inherited from the parent. That's why I can call all these different methods down here, right? So let's recompile this, clear up our mess here. Okay, so let's rerun our inherit1 program. We went back to what we did before. Here's the constructor of the parent and the child object. We then call F1, F2, and F3. As you saw in the main routine, all these are bar, my bar dot whatever. And you can clearly see that it printed out, hi, I'm F1 and I came from foo, because this is what we printed out in the F1 function in foo, that it was inherited by bar. Bar has his own F3, so bar is a superset. It has more stuff than just its parent. Later on, what do we do? Oh yeah, in the bar F3 member function, remember we printed out what J is and what A is, okay? And then when we destruct the bar object, notice the order of events here, all right? When I created a bar, the first thing that happened is the parent is constructed. Then the child is constructed. We then use it here. And when we destruct a bar, we destruct it in the opposite order. We destruct all the bars parts of the bar, and when we're done with that, we destruct the parent parts. Now, there's a reason we need to do this, all right? Order matters, okay? Because what would happen in this destructor, right, if I decided to print out the J variable in here? All right, let's just go ahead and cut and paste that from wherever we did that down here, okay? Let's just print that out right there. I'll print it out after I do this, okay? I'll just put an XXX so we can know that this is where that message comes from, so it doesn't look like the other one and confuse us, right? So when we destruct bar, it's going to print out this J. I cannot use the parent object if it's gone. Okay, so this thing is going to clean itself up and remove its member, delete, whatever. If you have, dynamically allocated memory objects and things, all that would be cleared out in here. Then when that's completely done, the parent will be cleaned up. And we do this because you might need to use things that you've inherited during the destruction of the bar, right? So let's go ahead and run that one. And obviously we can say, oh, I'm destructing bar. And before I finish destructing the child portion of the object, I can still play around with the values in the parent. When that's all done, the parent is then destructed. All right? So what do we get out of this? We get out that to subclass, as we say, an object like foo, you just simply say public foo. And the word public right here, by the way, says, look, anything that is public in foo is going to be public in bar. You can, if you want to, reach in here and say private. Okay? If I did this, then what would happen is all those methods that are inherited, like F1 and F2, will no longer be public methods. All right, I won't be able to do this down here. So let's compile that and show you what happens. Oops, if I can type correctly. Now it says, oh, it's inaccessible. It's because it's private. Hey, it's inaccessible. Same with the F2, right? That's because I said, go ahead and grab all the parts of foo, and even if they're public or not, make them private when it's presented as part of a bar. Okay, It's very common to leave public things public, but sometimes you have a reason to change that around, all right? Let's look at this one. Same foo, same bar, but this time we now have a baz. Just like the fruit example I gave you earlier, we could say, look, an orange is a fruit, but not all fruit is orange. Because you could also have a banana. A banana is a fruit, an orange a fruit, but given a fruit, I don't necessarily know what kind it is. So what we have now is a kind of a family tree. A foo has a bar, and now it has a baz. Now a baz just have a constructor and a destructor. We don't need to add all the other stuff and clutter things up. I just wanted to show you what happens if you create a foo, right? A foo can live on its own. It's a complete class, what we call a concrete class. We have a bar, which is a child of foo, and then we have a baz. And because baz inherits all of what foo is, it too has an F1 member function. So let's make sure this one works now. What happens here? Here's our foo that we saw from the first example. Here's the construction of the bar, the calling of the three methods in a bar. And remember, when bar's F3 gets called, it prints out these values, right? Now here's the new part. I construct a baz, and just because just like the bar, the parent of the baz has to be constructed before the constructor of the baz runs, okay? And you remembered seeing that we called F1 on the baz object, which is inherited from foo. And we now leave these all going out of scope. And they go out of scope in the opposite order that they're created. So again, there's another level of order here. If I create an A and a B and a C, it's going to delete them in CBA order, right? So the last one constructed, which is this stuff here, is the first one destructed when it goes out of scope. Okay, this one right here, these two lines are the destructors that are associated with, oops, I highlighted the wrong ones. These two here are the lines associated with destructing the baz, right? Because we just talked about how the bar has to delete the bar portions of that object before it deletes the parent stuff, right? So here's the baz getting destructed. Here's the bar getting destructed right here. And here's the foo being destructed that we created all the way at the beginning of main, all right? So what's the takeaway here? Well, you can have any given base type can have multiple different types of subtypes. All right, what was that? That was number 2. Let's see what number 3 has in store for us. Oh, it's going to start getting interesting. So we have the same foo that we've had all along. Here's the bar. Look what's happening inside bar here. We call this one an override, F1, in the parent object. Oops. Which is the foo class, right? So when I inherit everything, I can say, you know, I want everything that is a foo, but where F1 is concerned, I want to have my own F1, all right? Baz is unchanged, and now what happens here? Look what's going on down here. So we have two different things going on. Let's comment out these other guys so that it's easier to see what's going on in our output. Okay. We're going to create a bar. Let's comment this out too, because that'll be confusing as well. So we're going to create a bar. We're going to call F1, F2, F3. And because bar provides an override on F1, you will see that it calls the one in bar in this case, rather than the inherited one in foo. So the first thing that happens here is that foo is constructed along with the bar, because that's what bar was inherited from. Then we call myBar.F1. And unlike before, since bar has his own version of F1 that overrides the one that he inherits, it's going to call the one in bar right here. Then we call myBar.F2, and he gets the inherited one, and then he calls myBar.F3 because bar has an F3 and F1 doesn't even have one. So this was added to, it's augmented the parent object. And again, when we called F3, it prints out some extra variables. Then it goes out of scope, and the bar part of the object gets cleaned up, and then the parent part gets cleaned up, as you would expect. All right, so let's go ahead and put this thing in here. This is a new notation maybe to some of you. This thing here, if I know that I want to call the F1 in the parent of the bar object, I can do that if I want to. This is called the scope resolution operator, the 2 colons here, if you didn't know that. So what I'm really doing is saying change the scope of F1. Don't use the one in bar, use the one in foo. So if we compile this and then run it, we can clearly see now the foo version gets called. All right, so even if you override it, there's ways to choose which one you want to invoke. All right, I'm going to leave this other stuff commented out. It's just there because it carried over from the previous example. All right, so let's look at this last one here. Now what's going on? Here's my foo, no changes. Here's my my bar. And this is no changes from the last one, right? It has his overridden F1, and he's got his F3. Here's the baz in here. No changes from the previous video. And now we have this function in here. Look at what's going on in here. I've got a lot going on here, all right? So this is everything in the previous demo plus a little bit more. Let's see what's going on here. I can create a foo. You've seen this since the first demo, right? Then I can create a bar. And I can invoke F1. I can use the scope resolution operator and say, yeah, I know you overrode F1, but I really want the one from foo. I can do that and call the other ones. Now we're going to do something else right here, all right? Let's, well, before we get to this, let's wrap it up down here. This is the baz down here, no changes there. And we do, we call this new func thing. Look what's happening here. I call func and I give it a pointer to M bar, which is of type bar. I call it again, and I'm giving it the address of this foo up here. Look at this. I'm giving this, I got one function, and in here I'm passing in a pointer to a bar, and here I'm pointing it a pointer, passing it rather a pointer to a foo, and down here I'm pointing it and here I'm passing it a pointer to a baz. All right, so what's up with that? No matter what, I'm passing it a pointer to 3 different kinds of things, and yet everybody seems to be okay with that, as you'll see when we compile this thing. So what does this function do? Well, he takes a pointer to a foo, and if I want to, I can cast it to something else. Let's say I'm really smart and I know, even though somebody passes this a pointer to a foo, I know that the foo that's passed to this function should always have been created like this, because a bar is a foo, right? I can always do this. Well, let's make it simpler. I can always call F2, even if it's created as a bar, or I create a baz. They're all inheriting all that is a foo. So technically, let's comment this screwy stuff out down here. We'll come back to this in a minute. It's an example of bad code anyway. So here's what's going to happen, because a baz is a foo, and I pass at one point a pointer to a baz in here. I pass a pointer to a foo, right? Right here. I pass a pointer to a bar, and so on. All 3 of these different types I can pass to this function. The function says anything that is a foo, I will accept. All right, that's what this really means here. I want a pointer to a foo, and anything that is a foo is still a foo, even if it's a bar at the same time. Now, I purposely called F2 right here because the foo type has an F2, and I never overrode F2 here. I never overrode it in a baz. So if I call func and I call F2, or inside this thing using that pointer, this will work perfectly fine, because all of those are really a foo anyway. And if we sift through here, Always good to bash your head into the microphone. If we sift through here, we see foo F2 called here. We see it called twice inside these asterisks down here, and we see it called again down there, right? So let's concentrate on what's in these asterisks, right? So between these rows of asterisks, it got called twice, one for the bar and one for the foo itself. And in both of those, it just printed out, hey, I'm happy with this. I executed F2, and it makes perfect sense, right? Now let's go back to that other idea I was talking about. If I'm smart, or if I think I'm smart, that's your first danger as a programmer. If you ever think you're smart, right? That gets you in all kinds of trouble. You can cast this to a bar. Say, well, if I know this is supposed to be a bar and I got a foo, I can do this. Now, this is more important later on when we talk about virtual functions, okay? But conceptually, without all the noise of what it means to create polymorphic types using virtual functions, let's just focus on what this is doing in the pitfalls, all right? If I want to say, I want to call F3, and I tell people I declare this as a foo. I really should declare it as a bar if I really want to use it as a bar in here. And then the compiler will give anyone an error that passes me anything but a bar. But we'll soon see that this technique is useful in certain circumstances, all right? So let's focus on exactly what's going on here rather than the fact that this is just insane, okay? It's a great insane example that we can all understand immediately out of the gate before we muddy the waters, okay? So what happens if I cast it to a bar? This is actually perfectly reasonable if and only if it really does point to a bar. And I can then call P bar right arrow F3 like this. And this is perfectly reasonable in this one case right here. It is not reasonable here, and it is not reasonable there. So let's compile this and see what happens. So this is inherit 4, right? Let's run it. What do you think is going to happen? Are we going to crash? I don't know. Well, it didn't crash. What did it do? Well, here's the asterisks, right? And inside here, we called that func function. In fact, we call it twice. So the first time we called it, let's take another look in here, review. First time we called it, we did what I would argue is the right thing. We called func and we gave it an address of a bar, which is a foo. Therefore, the compiler is satisfied here. We call F2 here. And then we call F3 down here. There's a lot of noise. Let's comment out this thing. I can do it again. So now when we call func, it will only call F3 right there, okay? All right, let's clear this up, get some nice output. Okay. All right, the program runs, blah, 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 blah. We print out this row of asterisks. So we know this and this are the F3 calls that are made from that func function. Now, the first one makes sense. Remember, every instance of bar in the constructor, we set A equal to 123 here, no matter what, and we never change it. We mentioned that earlier, okay? So this actually looks like it's doing the right thing. And J has a value, and remember the J changes. We multiply it or add values to it and stuff like that because of other functions like up here when we call these, as you recall, the foo base class manipulates J. So we can see that changing. And we've seen this before. In fact, if you look at the 203 here, it's the same one that you see right here, okay? Because we properly called F3 on the bar object before we passed it into the func. So this here is circumstantially providing evidence that we're doing the right thing when we passed it in. Now let's look and see what happened down here. Remember, the second call to func passed it a pointer to a foo. A foo is not a bar, right? All fruit are not oranges. Yet this thing ran. Not only did it run, it called the bar F3 method. I mean, that's kind of wonky, right? How do you even call the bar method on an object that doesn't even have an F3? Okay, I'll leave that as a as a task to the viewer. Nonetheless, the compiler does this because we told it to. All right. You'll notice that this J and the A value are complete crap. It is not possible in the code that we wrote for the A member variable of any bar object instance to ever equal 2. So this is completely broken output. And it's because we lied. We said, assume that whatever was passed into func is a pointer to a bar object. And as I said before, no bar ever has an A that is any value other than this 123 right here. We never modify it, any of these members, and it's private. So how did that ever happen? I don't know. This is corruption taking place. I lied about the type of thing this points to, and the compiler takes my word for it, because that's what a cast does. It says, don't complain, just do this. Okay, you said so. And as long as it's right, this works. But when it's wrong, anything could happen. So when I call this, I lied and everything broke. My comment here is that this is okay to the compiler, all right? I should say that in parentheses, to the compiler. Because func wants a pointer to a foo, and the compiler's satisfied right there. Same thing with baz, okay? So after the whole thing is done, before we see all the destructors running, we pass it a baz. Well, what happened down there? Well, it gets called again, and now we got a 999 in this A field, right? So the only one that we know is correct is when we actually passed it the pointer to the right kind of thing. If we lie and tell it to accept our lies, everything breaks. And this is, this is a huge pitfall in design of C++ applications in general. Okay, you make this kind of mistake, and the compiler can't help you because you told it not to. And these are really difficult to debug. All right. Sometimes your program will crash with some obscure seg fault. Other times like this, it'll go and it'll just say, well, there's garbage data in memory somewhere that happens to look like where I'm looking for the value of A, and it'll print that out. Okay, great. This is a problem, a form of corruption. All right. Now, this will come back when we talk about virtual functions and abstract classes, all right? But this is the general overview of what happens with inheritance. So what's the takeaway here? The takeaway is any object can have and can inherit, we say, all the attributes of a parent class, all right? And any class can have more than one child objects created from it. You can even have transitive ones. If I wanted to, I could change baz to be a bar. All right. Now, what does that mean? Baz is a subclass of bar. Right? Bar is the parent of baz now, and foo is the grandparent of baz. So now I've got a 3-level hierarchy of inheritance. All right, now this will probably still run because it didn't change that much. All right, I'm not sure yet what this all means because we just arbitrarily changed this program in a major way, or conceptually major anyway, just to show that, yes, you can have multiple level hierarchies here. Let me put this back before I forget, and my notes are all wrong. Actually, this is really no big deal. This case would simply, what would it do if it was inherited from bar, right? It will construct this. I have no initializer list. So up here, it would have to construct its parent bar object with the default constructor, which is fine. And this then would go on to create its parent and keep on going. I guess this is an interesting example. Always risky to call an audible in the middle of a lecture. But what the hey, it's late in the semester. We can get away with this, right? Don't tell anyone. So let's look closely at what's happening down here. Remember, after the asterisks is when we created the baz object. Look what happens now. Remember when we had the double? constructor when we created the bar, and it went up and created the foo to go along with the bar, which is right up here. When I create my bar, it has to go up and create the parent first. Well, look what happens now with a BAS. Here's me creating the BAS, but before that, the bar object has to be constructed, right? And before that, the foo object has to be constructed. Oh, so all three of these then run before it can call F1 and pass it to func. And you'll notice that now, since BAS is a subclass of bar, what was earlier illegal, I should say, or at least broken and ill-conceived in func to cast a BAS instance to a bar, now it actually does make sense. And you can see when we call F1 on BAS, and then we pass it, the same object, into the func subroutine, it works correctly, all right? Now, when we destruct the BAS goes, its destructor, then its parent, then its grandparent, in that order, okay? And then here's the bar object and its parent, and then the foo that was created at the top of main, all right? So these hierarchies can be very deep, and they very often are. You can have dozens of, the lineage on these things can be quite significant. Now, you can also do things like, XYZ in here. You can have more than one parent if you want. You can inherit all the stuff from foo. You can inherit all the stuff from XYZ, and you can keep on doing this, right? Now, this is a little bit new. If you're a Java programmer, this might seem a little weird. To have more than one parent. In Java, you can inherit from what they call interface classes, but you can't inherit from more than one parent class, all right? In C++, you can. And it's a merge of all the above. And all kinds of weird things happen. If both foo and XYZ in that particular example both had an F1 member function, it begs the question, well, which one of them gets called? All right, and there's rules for all that sort of stuff, okay? I just wanted you to see that. I'm not going to go into all the myriad of details on that. The point of this lecture is to make sure that you understand what happens, which one is of, for example, F1 will get called when you override it like this, and how then can I, if I want to, choose which one of the two F1 methods gets called when I have a class like bar that overrides the F1 in the parent object up here. Which one gets called when and why, all right? So that's the whole point of this thing. And of course, when you're casting your objects types, you got to be very careful. You need to check this before you do it. In the course website, in the notes on the course website, it does discuss a technique for this, all right? But it's not working with my compiler because I don't have something set up in here. It says right in here, if you read this section, that comment down there at the end is really important. Upcasting and downcasting. So this is what we were just looking at. If I have a pointer to some object and I cast it to some other object, what can happen, right? So we were just talking about that and ran some examples. Well, what can happen is, and they refer to upcasting and downcasting. It's perfectly fine to tell something that, to consider, in this case, a bus. The parent of the bus object is obviously vehicle. So we call that an upcast. If you say, take a bus and consider it a vehicle, right? Take an orange and think of it as a fruit instead of a more specific thing. That's perfectly fine, and it always works. But if you go the other way around, and you say, take a vehicle in this case, or a fruit, right? And then cast it and say, oh, it's all vehicles are cars. That might or might not work, even the demonstration I just showed you, right? So this one is more complicated. We call that a downcast. And of course, this will fail if you lie and you cast it incorrectly. Now, there is this thingy here, and we'll see this, and we'll use this in the next lecture. You normally don't see this unless you're creating these polymorphic types, right? Which is the bottom part of this web page. So If you're going to do this and you don't have a polymorphic type, you need a special feature enabled in the compiler, which is currently not on in the compiler that I'm using, so I cannot demonstrate this. So what happens is this is useful. Really, it's only useful, in my opinion, when we're dealing with polymorphic types anyway. So this is kind of a chicken and egg problem. Let's defer this conversation of this right here until after we talk about polymorphic types. All right? So I hope this is useful. Thanks for watching. See you next time.